Hi guys, welcome back. This is the third lecture in the series on solids. Today we're going to be looking at solids and their structures. So if we just recap on the last lecture, if you remember we looked at molecular solids and how they're held together by relatively weak dispersion forces, which means that things like iodine can actually sublime straight from the solid to the gas phase. We looked at ionic compounds and how they're held together by strong electrostatic attractions or Coulombic bonds. We looked at metals and how they are held together in a lattice structure with atoms surrounded by a sea of delocalized electrons, and we looked a little bit more at how those electrons interact and kind of considered band theory to explain why it is that some materials behave as a semiconductor, and that behavior increases as we ramp up the temperature. We also looked at covalent network structures and how they're held together by very strong covalent bonds forming what we call an infinite structure. So a diamond, for example, forms this covalent network structure, which makes it one of the hardest substances that we know. Okay, so before we go on, I'll just introduce what we're going to be covering today. So we're going to be having a look again at polymorphs, but rather than looking at the allotropes of carbon, we're going to be focusing in on silica dioxide, so looking again at the varieties of quartz that we have. We're going to be looking at packing structures of spheres and the qubit structures. We're going to be calculating unit parameters, unit cell parameters even, and we're going to look at the ionic model again and taking that a little bit further, and we're going to be looking at whether or not we can predict the geometry of our ionic compounds. So as we already know, polymorphs are minerals that have the same chemical composition, but they have a different arrangement of atoms within their crystal structure, which is what gives rise to their different properties, which is why, as we know, graphite is very different in its properties to diamond. So individual polymorphs are generally stable under different conditions, and I'm just going to use an example here from the geology world to just demonstrate this. So on the y-axis here we have pressure in kilobars, and we have depth in, here as well in kilometers, and on the x-axis here we have temperature. Okay, so this red line here is a geothermal gradient. Okay, so this is how temperature changes with pressure and depth as you go down through through the crust. Okay, so this is where graphite is stable, which is basically at relatively low pressures, but up to quite high temperatures. But diamond is stable in this little area here, which is basically high pressures and high temperatures. So we know that diamond is forming at depths of over 100 kilometers. This means that diamonds are actually stable and forming not in the crust, but actually in the mantle. And we find it in what we call deep kimberlite pipes. So these are deep intrusive bodies. So what happens with polymorphs is that you have transformations. So these transformations can either be displacive, so this involves the bending of bonds, and this tends to be instantaneous, or reconstructive. This is quite sluggish. It happens over long time scales and involves the breaking and the reforming of bonds. So we're going to focus in on the polymorphs of silica. So all silica minerals are basically what's known as tectosilicates. They all have exactly the same composition of SiO2 arranged in an SiO4 tetrahedra. Okay, so they all share all of their oxygens with 4 other tetrahedra. What's fascinating though is although all these minerals have the same SiO2 composition, we have a number of different flavors of varieties of silica dioxide. So we have our classic quartz, tridymite, cristabalite, and ceasite. We have different varieties of colors. So you saw amethyst the other day, and we also have rose quartz. And here on this side, this picture is an example of rose quartz. And we also have different crystal sizes, so things like jasper and agate. So if it isn't the composition that is different between these different flavors of quartz, which gives rise to all these different properties from colors, shape, and symmetry, then it must be the structure of the atoms in that arrangement. Okay, to remind ourselves, here is a picture of silica bonded in that tetrahedral arrangement. I've just drawn over almost my entire slide there, which has silica bonded with 4 oxygens. Okay, so quartz is by far the most abundant form of silica. There are 2 types of quartz. We have low quartz, which is trigonal in its crystal structure. It's also known as alpha quartz. And we also have high quartz or beta quartz, which is hexagonal in its crystal structure. They both have a helical internal arrangement. However, alpha and beta quartz are the left and right-handed forms of the screw of the rotation axis. Okay, so these will basically at 253 degrees Celsius, this is where we have the displaces transformation between low and high quartz. Sometimes low quartz will have a hexagonal structure. It shouldn't. It should be trigonal, because high quartz will leave its remnant structure, will leave its visiting card. We also have our different structures of quartz. We have cristabalite and tridymite down here at the bottom, typically formed from siliceous volcanic rocks, and tridymite tends to form very, very rapidly or from rapidly cooling rocks. Basically, the conversion from quartz to tridymite is a reconstructed one, so it occurs really, really sluggishly. As I said, it's found in rapidly cooling rocks. And we should actually note that the structure of cristabalite and tridymite, it's arranged basically with upward pointing oxygen in the tetrahedra being shared with the downward pointing oxygen in the tetrahedral layer above. Before I carry on, I just want to say there are different types of polymorphism that we can see, which I won't go into the details of, but you should be aware that we have something called order-disorder polymorphism, and that basically is where you have 2 different atoms distributed either randomly or ordered between different sites across the mineral. So an example of a mineral that shows this order-disorder polymorphism is potassium feldspar. So let's go back to thinking about our structures, and the way in which to do this is actually think of our atoms or ions as basically hard spheres. And we want to, especially our metals, we want to be packing in as many of those atoms in together. So we're increasing the number of nearest neighbours. They want to have lots and lots of friends. And so we want as high a coordination number as possible. If we assume, as it is an elemental metal, that all the spheres are the same size, we can work out the most efficient way for those spheres to pack together, and that's known as close packing. So to start off, we think about layer A. Okay, so we've got basically our balls over here. This is layer A, simple, packed in, close arrangement. Now, layer B, we're going to lay on our next layer of atoms or ions within the depressions of the layer below, and this is quite simple. This remains the same no matter how your packing structure is going to be later on. It's the third layer which causes the interest. Okay, so it's this third layer which can be laid down in 2 different ways, and the reason why is because there are 2 different types of depression. Okay, so we can either put the third layer above the empty spaces in layer A, which gives us a cubic close packing structure. So you might see this in copper or silver or gold. Okay. Alternatively, we can lay it up so the third layer actually sits above the spheres in layer A, and this is known as hexagonal close packing. So things like magnesium and zinc will have this hexagonal close packing. Now, our cubic close packing is by far the most common of this arrangement. So the coordination number is the number of the nearest neighbours, we've already said, and in both cubic close packing and hexagonal close packing, we have a coordination number of 12. Okay, we can draw our cubic close packing structure in a slightly different way. We can upturn it slightly, as you can see over here, and we can emphasize its symmetry by drawing what's known as the unit cell. So this here is that repeatable unit that we see in our crystal structures. We can have a face-centered cubic structure like copper or aluminium, and this has a coordination number of 12. Okay, so here is our face-centered up here. Or less commonly, we can have our body-centered cubic structure, and an example of this would be iron or sodium or potassium. And here's our example of the unit cell down here. Or we can have a primitive cubic structure, which is incredibly rare, as such is only demonstrated in polonium, and this has a coordination number of 6. Okay, so as we know from our ABA structures, we can also have hexagonal close packed structure. Diagram in the top right is a repeating unit of this hexagonal close packed structure. However, it isn't the smallest repeating unit, so it isn't the unit cell. This is the unit cell. However, it might be quite difficult to see, and I'll see if I can use my drawing skills to try and highlight it. Basically, if I draw like that and like that and like that, you might start to see this unit cell start to appear. It's kind of like a double Trivial Pursuit piece. Imagine it interlocking, and so it's got angles that are actually 60 degrees. Okay. So if you imagine drawing across here at the top, then you may suddenly start to see that structure. So this has a coordination number of 12. So what we might want to do is actually have a look at our cubic close packing structure, for example, and work out and derive the contents of that unit cell. So if we take copper, okay, we can have a look at that. Here we go. We actually have a face-centered cubic structure. So in the middle of each of our faces, we actually have an atom, and I'm actually missing 2. There should be 1 there, and there should be 1 there also. Okay, so that's good to note. Anyhow, so the atoms inside our cell not shared with any other unit cells equals 1. We don't have 1 sat in the middle. Okay, so atoms on faces shared by 2 unit cells count as half. We have 6, now that I've added these in as well, 6 that actually sit on those faces, counting as a half. Atoms at the edges and shared by 4 unit cells are rated at a quarter, and atoms, not atos, at the corners and shared by 8 unit cells are an 1/8. So we have 8 in the corners and 6 in the faces, so that gives us a content of 4 atoms. Now I'm going to say here that we can actually look at the cell in a different way by looking at a cell projection. So this is looking at it from the z-axis down onto an xy coordinate system. So as we can see here on this location, we have an atom basically in our bottom layer and our top layer. Here we have just an atom sat halfway up, and here we have a cell sat in the bottom and the top layer. Okay, and you can follow that through. It's just a different way of looking at representing our unit cell. Okay, so now we can think about calculating the density of our unit cell. So we already know from our previous slide that the number of atoms within the unit cell are actually 4. Okay, so here's our close packing structure, and this is the cube that we're trying to represent. Okay, I should actually highlight where I was talking there. So in order to actually get our unit cell density, we actually want to know the volume of this cubic cell. Okay, so what we can do is we actually want this length here. So how can we get that? So this is A here. Well, we've basically drawn a triangle, so we can use Pythagoras' theorem to actually work this out. So it's A squared plus B squared equals C squared. So our C squared is basically our 4 radiuses down here, or 4 radii, sorry, and we have A and A. So A squared plus A squared equals 4r. In other words, A equals 4r over the square root of 2. And then our volume will be A cubed. So now we want to calculate the mass of our unit cell. Okay, so that's basically our molar mass times by the reciprocal of the Avogadro's constant times by the number of atoms in the unit cell. And our result should be in grams per unit cell. And then, of course, once you've got mass and volume, you can calculate the density. Okay, so we already know our volume, A cubed, and it can also be written as 8 to the power of 3 over 2 times by R cubed. Okay, so we know the total number of atoms in our cubic close packing structure is 4. So we basically want to times the volume of a sphere by 4. Okay, so that gives us 16/3 times pi r cubed. So we can basically write our equation down here that we're basically just ratioing those two volumes. Okay, so we can calculate that the packing efficiency of a cubic close packing structure is 74%. So let's revisit our ionic model and looking at our ionic compounds. If you remember, we used a heat map generated from X-ray crystallography to calculate the ionic radii. However, why do ionic radii vary? Well, it depends on the compound that you're bonding it into, and also the coordination number that it's actually in. So how much of a pull does it actually have from our other ions within the compound? So I put here like ionic radii. I think I should have actually written like atomic radii. Ionic radii increases as you go down a group, as you're actually increasing another shell of electrons. And for isoelectric ions, so those that have the same electron configuration, the greater the nuclear charge, the smaller the ion. So the more sort of attraction to the nucleus, the smaller that ion is. And should be noted as well that anions are larger than cations. Okay, so this graph here on this on the right hand side shows our isoelectric ions going across from sodium to magnesium to aluminium to silica. Okay, very poorly drawn line there. So on the basis of the previous information, we can actually quite accurately predict the structure of our ionic compounds. So it seems like common sense to say this, but just need to reinforce this, that in ionic solids, ions are in contact with nearest neighbours that have the opposite charge because they're attracted to each other. This means the distance between those nearest neighbours is the sum of that ionic radii. Now, as we know, our compound is going to be most stable when it maximizes those anion-cation contacts. Okay, so when it's got the highest number of nearest neighbours or the highest coordination number, and because of that, we can actually predict our structures, whether it's going to be linear, trigonal, tetrahedral, octahedral, or cubic. Okay, and we can do this by looking at the ratio of our ionic radii which are involved within those bonds, and also by using the coordination number. We can very closely predict that geometry, that packing geometry around the cation. With that in mind, what is wrong with this diagram? So I was so impressed. I spent ages drawing it, and I went to do this, and I just went, what have I done? Can anyone spot the mistake? Yep. Okay, so I have actually got the anion in the center there, which was a bit stupid of me. So anyhow, so this table here shows our radius ratios, our coordination number, our packing geometry, and this little representation of how those shapes are arranged. And I should just point out that our octahedral structure is shown up here, and this is actually an example of halite or sodium chloride here. Okay, so in order to predict our geometry, we want to calculate our radius ratio. So how do we go about doing this? Well, here's a little diagram over on the right-hand side. What we have is our sodium cation in the middle and our negative chloride ions around it. So we can draw two triangles to try and work this out. So we've got our blue triangle. So this length here is the combination of the cation and the anion radius. And the hypotenuse here of the blue triangle is actually two times the radius of our anion. Okay, so I haven't put that on the slide there. Then our red triangle is actually half the size of that, so we've got an angle here of 45 degrees, and we have basically our opposite is basically the radius of our anion. And here we have the same length of the sum of our anion and our cation. So what we can do is we can actually use the sine rule to actually calculate our radius ratio. So what we know is that from the sine rule is that for any triangle with the side lengths of A, B, and C and angles of A, B, and C, that we have A over sine A equals B over sine B equals C over sine C. Okay, so we can apply this to this situation. So for our bigger triangle, we have the sum of our anion and cation radius over sine 90, and that equals the radius of our anion over sine 45 of the smaller triangle. Since sine 90 equals 1, okay, so our sum of our radii equals the radius of our anion over sine 45. You're following that? And then basically the radius of our cation equals the radius of our anion over sine 45 minus the radius of our anion. And that's also then equal to the radius of the anion times by 1 over 45 minus 1. So this means that our ratio of our anion cation is equal to 1 over sine of 45 minus 1. And we always will represent the ratio this way around, with the smaller cation above the larger anion. So in summary, we have covered silica polymorphs. We have looked at the close packing arrangement of spheres and thought about the different arrangements that there are. We've looked at the cubic structures. We've looked at how we can characterize and quantify the contents of a unit cell, so that little repeatable unit. We have looked at the ionic model again and looked at the variations in ionic radii, and then we've looked at predicting the geometry of ionic compounds from that ionic radii. And I hope you appreciate my little sketch here on the right hand side. So I look forward to seeing your lectures. Hopefully you've managed to survive all of my content. All right, cheers guys.